All right. So in the previous class, we were looking at a few applications of duality. And the last application we talked about was economic interpretation of the dual. So I want to say a few more words about that. Okay, so we want to essentially interpret what these optimal dual values mean, or the optimal dual vector means. So for the primal, optimal primal vector, there is a very clear meaning. In the end, we had this problem. So the primal problem was you want to minimize c dot x. Let's say we put it in standard form such that ax equals b. And then we had an additional assumption that this primal problem has a non-degenerate basic optimal solution. So this has a non-degenerate. So let's just think of this as being some technical condition. Of course, it is quite important, but for the moment, for our understanding of this, let's just think of this as some technical assumption. So as a general principle, we just say that, okay, every such primal has such solution. But the whole moral of the story was if you choose any vector t in Rn, and let's say you look at the perturbed primal problem. So you perturb it a little bit, meaning, so you look at minimize c dot x and you increase your resources such that ax equals b plus t. So x bigger than equal to 0. So the amount of resources you have, you increase. So intuitively, you feel that, okay, if the amount of resources you have is more, let's say t is a vector which consists of all positive entries. So in that case, b plus t will, so each entry of b will only increase. So in that case, your feeling is that your profit should also increase. So this quantity c dot x should also increase because the amount of production you can do will also increase. And it gives you precise formulation like the dual variable. So if c star is the optimal value here, so c star is, let's say, the optimal value. So that's the optimal profit you make. So the maximum profit you make. So I guess in that case, you'll put a minus c here. But in any case, so let's say c star is the optimal value here. Then for this perturbed problem, the optimal value will be c star plus u star dot t. So this will be the optimal value, where this is the dual optimal solution. That is the unique dual optimal solution. We had shown that if this has a non-degenerate basic optimal solution, then there is only one dual optimal solution. So you pick that one, that particular one, and you know how the profit is actually perturbed by this increase in resources. And if we write this out, so u star dot t term, this is nothing but summation I equals 1 to m uiti. So effectively it tells, let's say I keep everything constant except I change, so let's say t1 is equal to 1 and t2 is 0 and all the way up to tm is 0. That means you are not changing the amount of resources 2, 3 up to m, but what you are doing is increasing the amount of resource 1. So then this quantity right here, so in that case, you have, this is nothing but u1. So this is the value of the dual variable, like the first dual variable corresponding to this optimal solution. So u1 dual times t1, which is 1. So u1 dual, u1 u1 star, right? So the interpretation of this was if I increase by t by 1 unit, then this is increased by u1 star. The profit is increased by u1 star. So ui star was the marginal value of the ith resource. So marginal value of the ith resource. Of course, here I chose 1, but generally this theorem may not be valid for 1. You have to choose up to epsilon. But essentially it is saying that if you increase, so there is some epsilon, within which if you increase by an amount of, let's say, delta less than epsilon, then the change in the profit will be u1 star times that delta. Okay. And so of course, like here we're trying to give the economic interpretation of the dual. But if we had a similar problem, so what would be like such a perturbative theorem for the dual problem? There you'll change this cost function, right? So here you are changing the resources, So you're doing a B plus T. So in the dual, such a theorem would translate to something like C plus T. And then the primal optimal solution would, what would that say? What would be the economic interpretation of the primal? So essentially, so you have C1, so C dot X star. So this is the primal optimal solution. So primal optimal solution. So what this is saying is if I increase the cost by 1 unit, so let's say I increase C1 plus 1, and rest of them are fixed. So rest is C2, rest of the cost of the products are fixed. Then the amount of increase in this optimal value is just X1 star. So for epsilon increase in the cost, you'll get epsilon times X1 star. So economic interpretation of the primal is actually more obvious. It's just saying that if I have a certain cost associated with a certain primal variable, and I'm increasing the cost, depending on yeah, so if I'm increasing the cost, of course the profit is going to increase. And in the dual variable, you have a analogous statement. Okay. And the last thing was, here we were interpreting in terms of the LP in standard form, AX equals B, X bigger than equal to 0. But especially this economic interpretation where we're thinking of like increasing resources, there the constant will not be an equality. It will be like an inequality constant. That would be the standard way of putting it. So this was a mathematical result. We'll so look at what practically how the problem will look like. So it will look like, so maximize C dot X. So maximize this profit given AX less than equal to B and X bigger than equal to 0. So you'll have all inequality constants. Then you can easily reduce it to the previous form. We have already seen in some of the assignment exercises and so on. So what you do is introduce slack variables. And then what you have is AX plus identity. So you're adding. So this is like the first row plus Y1 is equal to B1 and so on. So it turns out to be AX plus I times Y equals B. And X is bigger than equal to 0. And also Y is bigger than equal to 0. The slack variables are going to be positive. They are measuring what is the discrepancy between AX and B. So now this is in our previous form. So if we are going to use that theorem, we'll say that if the above equivalent problem, so this problem is now equivalent to this, the cost function is still maximizing C dot X. So essentially your cost vector has become C padded with a bunch of zeros. So this transpose X padded with a bunch of Y's. So here your vector is X comma Y. You have these new variables, but the cost associated with them, you're giving 0 because ultimately your goal is to maximize this function C dot X. So if the above equivalent problem has a non-degenerate basic optimal solution, like I said, this is mathematically, of course, very important, but think of this as a somewhat technical assumption. Then the optimal value of the original problems, sorry, the perturbed problems. So max C dot X, and then AX is less than equal to B plus T. So here it will just corresponding to your adding B plus T in the right-hand side. So it will still be of that form. So this is this much larger. And that is because you can see that when we are doing this change of general form to standard form and so on, the optimal solution, those were vertices, they never changed. So in this case, so once you get an optimal solution for here, you can ignore whatever corresponds to Y, and then take those X's. Right. Yeah. In any case, for the dual, you may have two distinct LPs, but both of them you can transfer from one optimal solution to the other. So yeah. So this is what you have. The number of constants, as you can see, still remains the same, right? If it is m by n, and this is, let's say, m by m, so then this will be m by m plus n matrix. So the dual variable, it will still be in Rm. So those will be taking values in Rm. Okay. All right. So those are the final kind of tying up the loose ends. in the economic interpretation of the dual. And the third application, so this was the second. The first one was we talked about theorems of the alternatives, Farkas lemma 1 and 2. And we saw that using duality, we could prove those lemma, but at the same time, we could even do that using first principles and invert the logical arrow. So first prove Farkas lemma from geometric ideas, basic geometric principles, and then using Farkas lemma, try to prove weak duality and strong duality. So that was somewhat like the first circle of ideas as an application of duality. The second was this economic interpretation of the dual variables. And the third example, third and final example we're going to talk about is something related with game theories, the beginnings of game theory in some sense. So matrix games and the minimax theorem. So this is also known as von Neumann's minimax theorem, proved around 1928, I believe. Okay, so let's look at this example of a game. So you have X. So the game X and Y play is essentially they unknown to each other. They point a finger. Either they can raise one finger or two fingers. So X holds up one finger or two fingers. So they can't see each other. Their backs are facing each other. So there is a judge who decides or who is figuring out how many fingers each of them has lifted. So holds up one finger or two fingers. And Y does the same. Okay. Now what happens is if X and Y, after they have lifted, they can see what the other has done. That information they can get, but while doing that, they cannot see what the other is doing. Or you can just say they do it simultaneously. Okay, so if X and Y make the same decision, meaning let's say X puts up one finger and Y puts up one finger, or both put two fingers, make the same decision, then Y wins. Y wins 100 rupees. Okay. Now, if they make different decisions, then X wins. If X, Y make different decisions, for example, X holds up 1 and Y holds up 2, or X holds up 2 and Y holds up 1, then X wins. But here the thing is, it depends on what X and Y have done. So for example, so X wins rupees 100 if he put up one finger, if he or she put up one finger, and rupees 200 if they put up two fingers. That means Y has put up two fingers in the first case, and X has and Y has put up one finger in the second case. So here both cases X wins, but different amounts. So one win is more valuable than the other. Okay. So this, so we'll make a payoff matrix. So let's say A. So payoff matrix minus 100, 200, 100, and a minus 100. So how to read off this? So this column corresponds to X showing one finger. And this corresponds to showing two fingers by Y, this row, and this column corresponds to showing two fingers by X. So what is this minus 100? So the entry Aij is how much X pays if X shows ith finger or jth finger, and Y shows ith finger. So for example, if for the diagonal entries, so X shows first finger and Y also shows first finger, one finger I see. Instead of jth, let me just say J fingers. So if both of them show equal, Y wins, right? So X has to pay some amount Okay, in that case, let me just say how much y pays. So X does not have to pay anything. In fact, he gets 100 rupees. So I'll call it y pays minus 100. So in this case, y gets 100. Okay, but in the other case, this point is what? 2-1, 2-1th entry. So y shows uh, 2 fingers and X shows 1 finger. Yeah, so that is rupees 100. So y pays rupees 100 and here y pays rupees 200. So this matrix A for this sort of game is called a payoff matrix. It decides after the end of the game who gets what. Okay. Now, so if X, so now they have to make a strategy to win as much money as possible. They'll be playing this game over and over again, and they both want to make as much money as possible. So typically in a game, it's going to be a dynamic game. Like if it's a static game, like in the sense X thinks, okay, if I put up, um, so so X says like anyway, if we make the same decision, I'll lose 100 rupees. But if I put up 1 finger and then Y puts up 2 fingers, I win 100. But if I put up 2 fingers and Y puts up 1 finger, then I win 200. So anyway, if I have to make one choice, I should make it to be 2. So I should put up 2 fingers no matter what, and then I will either win rupees 200 or lose 100. But if I put up 1 finger, I either win 100 or lose 100. So I will lose 100 anyway whenever I lose, but at least I can maximize my profit. So let's say X decides on that strategy. Every time he'll put up 2 fingers. But then after 2 or 3 rounds, Y might make a guess that, okay, it looks like X has a pattern, like X is always putting up 2, so I'll always put up 1. So Y is also pretty clever. So if X has a very strict strategy, then Y will eventually just start winning. And similarly with Y, if X notices that Y is using the same strategy, then X will always win. Okay, so both of them have to have mixed strategies. So okay, let me write down. If X does the same thing every time, does the same thing, meaning either always puts up 1 finger or always puts up 2 fingers, and Y sees the pattern, Y will do the same and win every time. And conversely. Okay. So yeah, if Y does the same thing, then X will just do the opposite and always win. Okay. So both players, so the moral is both players must have a mixed strategy. Must have a mixed strategy, meaning they will sometimes have to put up 1 and sometimes have to put up 2 fingers. But how do they determine that? Like when to put and when not to put? They'll probably roll a die or something. And also, choice at every turn must be independent of past turns. Why so? Because if there is a dependence, that means based on the past, you can predict what he's going to do. So after enough observations, Y would have noticed, okay, X, there is a pattern. There is some dependency relation between what X does in the past and what X does right now. So I can, if I can model that, I can predict what X will do next. So choice at every turn must be independent of previous turns. Must be independent of previous turns. Okay, so here the mixed strategy would be the following. So X puts up 1 finger with probability X1, and they have a, let's say, a random number generator or a random probability generator based on these probabilities. So random number generated based on the probability. So with probability X1, let's say, and X puts up 2 fingers with probability 1 minus X1. So with probability, you could say X2, which is equal to 1 minus X1. And the strategy is essentially, essentially like with probability x1, like I put up one finger, or with probability 1 minus x1, I will put up two fingers. And which one to choose, you just, let's say maybe you have a Python script or something which are seeded with these type of probabilities, and it is returning values 1 or 2. So whichever value is returned, you just put up that many fingers. Okay. And so this will be done randomly and independently of what you have done in the past. And y will also have a similar strategy with probabilities y1 and y2, which is equal to 1 minus y1. Okay. Now, so on average, if y puts up one finger, so let's say y puts up one finger all the time, then how much does x win on average? Like, what is the expected value of the win? So if he has put up one finger, then he'll lose 100. So x will win. So minus 100 x1. So he'll lose minus 100 with probability x1, and he will win 200 with probability x2, which is nothing but 200 on average. So that is the expected value. And if y puts up two fingers all the time, so if x is just following this mixed strategy, of course, if y puts up two fingers all the time, like I said, x now knows that uh, uh, he should be putting like one finger, the opposite. So x will win 100 x1 minus 100 x2, which is nothing but 200 x1 minus 100 on average. So here is what x thinks. So x reasons. So I have this mixed strategy. After some time, so this is like a frequentist approach to statistics, right? You make some observations, and you, to guess the probabilities x1, let's say you, after you played this game 50 times, and you notice that x put up one finger 10 times and put up two fingers 40 times. So that means you've figured out that, okay, with probability 1 over 5, x is putting up one finger, and with probability 4 over 5, he's putting up two fingers. Okay. So x is thinking, okay, and y also knows what I'm doing, right? So y will be able to guess x1, x2 after some games. So again, this is the frequentist approach to statistics. Okay, so then he says, okay, so I have these two sort of payoffs. So then so I have not made my choice of x1 yet. So whatever choice of x1 I make, these are the average values I'll be winning. So what I want to do, so x wants to choose x1 to maximize this 200 x1 minus 100. So after y figures out the strategy, so whichever is more favorable, y might choose that. So if y puts up one finger, y realizes, okay, I'll be giving this, but if I put up two fingers, I'll be giving x this much amount. So I want to minimize that. So in that case, y will choose to minimize that. But then what x wants is, okay, y will do that. So from that minimum, I want to maximize that minimum. So I want to maximize this value. If y chooses to make a strategy of whether to choose one finger or two fingers based on this, minimizing this quantity, minimizing my profit, then I want to maximize that minimum. So this is the x is reasoning. I want to maximize this quantity. Now y reasons. So y thinks about this and says, so if I put up one finger, so this is what y is thinking. If I put up one finger with probability y1, probability y1, then x will win minus 100 y1 plus 100 y2. by repeatedly putting up one finger. Okay. And then similarly, if I put up two fingers, and similarly, if I put up two fingers, X will win 200y1 minus 100y2 by repeatedly putting up two fingers. So both of them are trying to outsmart each other, like second guess each other, what they are going to do. So here, X wants to maximize, even with all the knowledge Y will get, X wants to maximize whatever he'll get. And Y says, I want to give as little as possible. So if I do this, yeah, so you have this maximum. So X will make a strategy which will maximize this, minus 100y1 plus 200y2 and 200y1 minus 100y2. And Y wants to minimize this quantity, minimizes the quantity Y will give. So note that these are two different perspectives. So actually so this Y reasoning, I could have actually replaced Y with X and done the same reasoning, which will be different from what I have written for X reasons, right? The first half is essentially saying that I'm thinking about what Y will do and I'm trying to maximize my profit. But the second part is I'm trying to minimize my loss. So first is maximize my profit in the safest possible manner and minimize my loss. So the formulations of these two strategies look actually quite different. Maximizing profit versus minimizing loss, right? So perhaps the second part also I should have said X reasons and done the same process. Now, as it will turn out, that actually both strategies give you the same answer. So maximizing your profit or minimizing your loss actually give you the same answer. But a priori, just looking at this strategy, it is not very clear that that is the case. Because in the first case, I'm trying to say, okay, Y will do this. And so after some time, Y will be able to guess my mixed strategy. And then whatever is my expected cost for Y putting up one finger is this. So Y will essentially decide to minimize my average income. But then I want to choose X1 such that I will maximize that minimization. And then the other reason is not to maximize my income, but rather to minimize my loss. So then I'll think, okay, X will start thinking, okay, if I put up one finger repeatedly, then Y has this mixed strategy. So Y will win minus 100y1 plus 100y2. Yeah, and if I put up two fingers, Y will win, so and so. So you want to minimize your loss. So what duality will tell us that max min is equal to min max. That means maximizing your profit is, in this matrix game at least, in this particular formulation of the game at least, that maximizing your profit is same as minimizing your loss. Okay, so let's look at a general matrix game. So this was like a 2x2 matrix game. So general matrix game, essentially you have a m by n payoff matrix. So this is your payoff matrix. And there are many decisions you're taking. So decision here was one finger versus two fingers, but there could be n decisions that you're taking. And from that decision space, so, your adversary Y is also making some decisions. And yeah, so in one strategy, you want to maximize your profit. And in the other strategy, you want to minimize your loss. And without loss of generality, actually in this payoff, I can always add alpha to every entry. So the values, the optimal values, or let me not use the word optimal, the values of x1, x2, y1, y2, and so on are unchanged if one adds alpha to every entry of A. So essentially you have changed the payoff. So that's because no matter what you do, so here, So let's say I increase y1 plus alpha, then I'll get something like that's because y1 plus y2 is 1, right? Okay, so sorry, this needs some justification. So let's formulate the problem. So essentially, this is what we want to solve. So find alpha in R and X in Rn such that you have this linear program 1, which is maximizing alpha subject to Ax. So X is the probability, vector of probabilities. And this has to be bigger than or equal to alpha times E. This vector is just ones, consisting of ones. So this is essentially minimizing the maximum. So you have all these options, like so each of these entries, 200 minus 300 x1, 200 x1 minus 100, all of them were in this column, and you want to find an alpha which is less than or equal to all of them, and you want to find the like greatest lower bound in that case. So the reason why we are using this vector E is because we want that alpha to be bounding all of the entries of this matrix AX. So each of the entries of AX essentially corresponds to these values. Okay, and you want a minimum of that. That is alpha. You want to find this alpha, and the constraint is that E dot X is equal to 1 because this is a probability way. So E is just 1, so it's essentially x1 plus x2 all the way up to xm is equal to 1, and X is bigger than or equal to 0 because it's a vector of like probabilities. It's a probability vector. So you have X bigger than or equal to 0. Now X's goal is to find beta in R and Y in Rm. So this is Y will give the strategy of Y. So X will give the strategy of X, this probability vectors, and Y will give the strategy of Y. So X's goal is to find the strategy of Y. So he wants to minimize beta such that Y transpose A is less than or equal to beta E transpose. And this, if you interpret, you'll be noting that you'll get these numbers. And again, inverting that problem, you just see that you want to maximize all those numbers, like all the entries. So the maximum, if it is beta, then you can have a uniform bound, beta times E transpose. And this is, by the way, the sizes are different. Here, E is actually in Rn. Here, it will actually be in Rm. But just abuse of notation a little bit. Okay. And yeah, so this I can formulate as you want to minimize minus alpha, and here you want to maximize minus beta, right? So notice that these are actually dual problems to each other. So if you formulate it the right way, so this is P2. Let's call this P2. P2 is in fact dual to P1. And that you can see because so think of these as consisting of variables x, x1, x2, xn, and then you have this extra variable alpha. So if I move the alpha here, essentially, so you'll have something like AE times x alpha. So this vector x alpha is bigger than or equal to, perhaps I should put a minus alpha here, is bigger than or equal to the 0 vec. So think of this as your new matrix, and this as your new vector, whose last coordinate I'm denoting by alpha. Similarly, what I will do here, I will consider y beta here. And of course, cost vector you can imagine is like 0, 0, 0. At the end, you have a minus 1. Or if you're trying to minimize minus alpha, at the end, you just have a plus 1. Yeah. And this also you can pad up here. And if you look at the dual problem, it will precisely give you this. And so yeah, so you have this bigger than or equal to sign here. So in the dual, you will have less than equal to, right? The sign will invert. No, sorry. The corresponding dual variables, you will have this sign constant, y bigger than equal to 0. And then if this is equality, so this is an equality right here. Yeah, let me just take a look at that. Yeah, so anytime you have equality, you have an unsigned constant. So this will correspond to beta unconstrained. So x bigger than equal to 0 will correspond to beta being unconstrained. And these inequalities right here will correspond to y bigger than equal to 0. And this sign constant will correspond to y transpose A being less than equal to beta E transpose. And then, of course, the vector here. So here, the vector is nothing but 0, 0, 0, all the way up to 1. And if you look at the coefficients here, that's exactly what's happening. Everything is 0, except there is 1 here. So that is your vector B. So once you notice this, like Minimax theorem is borderline like trivial. Once you have studied duality and you notice immediately that P1 and P2 are dual to each other. So this implies like optimal value of P1 is in fact equal to the optimal value of P2. So it doesn't matter which strategy you build up, either you maximize your profit or minimize your loss, you'll end up with the same answer. So this theorem will be yeah. So max of min is equal to min of max. So this is the von Neumann's minimax theorem. And this also actually gives you a strategy to figure out Y strategy. What is the Y's optimal mix strategy? So note that here, if I solve this problem, then I will also get this optimal value of Y. So I actually know what are the probabilities Y is going to use, and Y will also know what the probabilities I'm going to use, and that will make no difference. So X will have, so X and Y will have full information about each other's mix strategy. About each other's mix strategy, but still, like the profit or loss they make will be independent, like will not be affected by the fact that they have full information about each other's mix strategies. Okay. All right. So this is where I would like to end with like linear programming, so to say, the linear programming part of the course. And from the remaining, let's say about a few weeks, 3 weeks maybe, of course, we'll move on to this more general phenomenon. So we'll not be doing it in too much detail, but it is coming back to a point I had mentioned in the first lecture, that the great watershed in optimization is not between linearity and non-linearity, but it is between convexity and non-convexity. So in fact, whatever we have seen, like generally, so this is taking us back to our first lecture where we said optimization is a very broad term, right? So optimization, you have this objective function on some space, and X belongs to some D in Rn. So this is my decision space. And this is my objective function. And I want to minimize this. And then depending on what is the geometry of this space and what does this look like perhaps it is unconstrained, like it is all of Rn. So depending on what D looks like, so our strategy to optimize F naught depends on both the nature of F naught and also D. The nature of F naught and the nature of D. So the case we have been doing so far in linear programming, simplex method, and so on, is our objective function was linear or affine, if you want to add a constant, but anyway, that did not matter. But it was something affine, and your decision space was in fact a polyhedron. So you had very specific structure, and we exploited that a lot. The fact that it was a polyhedron, it had some extreme points, extreme rays, and so on. So those are the things that drove our strategy. So as you can guess, that as the nature of D changes and as the nature of F naught changes, the strategies must change. So it might feel like, okay, I mean, this is pretty much like quite ad hoc. Like I'll change my nature of my function, change the nature of my decision. Are there some general principles? So that's the first question comes to mind. So from linearity to non-linearity, which way do I go? So what is the right um, like right level of generality which will still preserve the theorems that I have had so far? So it turns out that convexity is the right amount of generalization. If I generalize too much, like saying that, okay, F naught is smooth, it's just too broad. But convexity is the right amount of like generalization where you'll still have viable strategies to solve this optimization problem. So I'll just quote that again. So in fact, the great watershed in optimization is not between linearity and non-linearity, but between convexity and non-convexity. Linear functions are of course convex, between convexity and non-convexity. So this is a quote by Rockefeller, 1993. So already I had mentioned this in the very beginning of this course. So our next goal is to talk about D being convex sets and F naught being convex functions. And what happens is the Minimax theorem we just saw, and the notion of duality and all of this, there is a notion, a corresponding notion for this type of problem where F naught is a convex function and D is a convex set in Rn. So that is known as Lagrange duality. So mostly I'll be following chapter 3 of the book by Boyd and Vandenberg, Convex Optimization. And also for the more rigorous mathematics part, I'll be using convex bodies, the Brun-Minkowski theory. So Snyder, section, I believe 1.6. Okay. So here we'll be dealing with objective function being convex functions, and our decision space is a convex set in Rn. Typically, it will have non-empty interior. Non-empty interior. Okay, so this brings us to the area of convex optimization. And just to repeat, many of the phenomena that we have seen for linear programming will also say similar. Of course, they will not be identical, but like we had a weak duality and a strong duality theorem, we'll still have, once we introduce Lagrange duality, and especially this is relevant because you have been studying analysis 3 this semester, which is talking about multivariable calculus. And if you think about it, even in your 11th and 12th, I should say 12th standard, you have done optimization problems, right? For example, maybe in your 12th textbook, it was there, okay, you have this square cardboard of length 1, and I want to cut off the edges of length, so squares, cut off the squares and fold it into a box. How do I maximize this volume? So essentially the volume will be, you have this is 1 minus 2x, and here this is the height is x. So it will be x times 1 minus 2x whole squared, and x lies between 0 and a half. And you want to maximize this function. You may remember in your high school, you have faced this problem. This is also an optimization problem, right? Your decision space is an interval 0 to half. So D is in fact 0 to half. I'm not saying this is convex. I'm just saying that this is in general. Of course, I don't think this is a convex function. You can check it out. But this is just to tell you that optimization is not something new to you. You have already done it, but this was something like a global optimization. So you had a certain smooth function, and you want to maximize this between 0 and half. So you take derivatives and compute its set it equal to 0. So in the interior, you find such values, and if not, then you check at 0.5 at the endpoints, whichever gives you the maximum value, that's what you choose. Typically, in this case, if you choose 0 or half, the volume will be 0. So you kind of intuitively know that the optimal value or the maximizing value of X is in fact somewhere in between. So when we talk about optimization in general, so multivariable calculus will start playing a big role. So for example, if you have smooth functions, we'll be taking gradients and setting things to be equal to 0. If it's unconstrained, meaning d is equal to Rn, so that is pretty much all you can do. I mean, and you just hope that local optima kind of tell you something about global optima. And precisely, convex functions have that very special property that there is typically a unique local optimum, like optimal value, I should say, because you can have a flat like plane like this, or if you're thinking in one dimension, this function is a convex function, fx equals just a constant. So, but the optimal value is unique. The optimal solution may not be unique, but the optimal value is unique. And the great thing about convex functions is that they always have a unique minimizer, minimizing value. Okay. But of course, I've been using this word convex, and so let me define it properly. So convex sets we have defined. We have studied convex geometry quite carefully. So now is the turn to study about convex functions. So like I said, we split the problem into two parts. So D, we have actually a pretty good handle. Convex sets in Rn, what do they look like? We had all these representation theorems using boundary points and extreme points. And we also had representation theorem using supporting hyperplanes. So D, we think we know pretty well. Now, what about F naught? So we'll start talking about F naught today with the 10 minutes we have left, and we'll keep talking about convex functions next Tuesday. And then once we feel like we understand convex functions really well, then we'll start talking about optimizing convex functions. All right, so let's start with the definition. So let's say omega in Rn be a convex domain. So convex domain would mean it has something, some non-empty interior. So F is said to be convex, said to be a convex function if for any 2 points in omega, if for any x1, x2 in omega, and lambda in 0, 1, we have f of lambda x1 plus 1 minus lambda x2 is less than equal to lambda f of x1 plus 1 minus lambda f of x2. So pictorially, so you have, let's say in R3, you have a convex function on R2. So what's happening is if I take any 2 points in this convex set, so let's make this a bit more convex looking. And if I take 2 points here, then the value here, so if I join the line between the values, so let's say this is the third dimension. So this is the height. So f of x, x1, this is f of x2. Then, so this line is in fact bigger than the value here. So if you take z here on this line, then f of z is in fact less than equal to the value on this line at that point. Or if you're thinking in one dimension, if you have a function like this, you take a point here, I take a point here, this function would be said to be convex if I take any point in the middle that is less than equal to the line joining these 2 points. So note that the right hand side, lambda fx1 plus 1 minus lambda fx2, the graph essentially represents this line. It's all convex combinations of x fx, x1 fx1, and x2 fx2, right? If I take convex combination of this, then I get lambda x1 plus 1 minus lambda x2, then lambda f of x1 plus 1 minus lambda f of x2. So convex combination of these 2 points in the graph. So this is representing this line segment that always lies above the curve. So which would mean that this quantity lambda fx1 plus 1 minus lambda fx2 is bigger than equal to f of lambda x1 plus 1 minus lambda f of x2. So let me just quickly define something known as an epigraph of f. So epigraph you can define for any function. So epigraph of f is equal to x xi in Rn cross R, such that f of x is less than equal to xi. So f of x is the value of x. So x fx will be the graph. So x, the epigraph is essentially all those points above the graph. So all points in Rn cross R lying above the graph of R. Graph of f, sorry. So you plot the graph of f, take all points which lie above that graph. That is precisely the epigraph of f. And from this discussion, it is clear that f is convex if and only if the epigraph of f is convex. So in fact, the name convex for f comes from convexity of a set, right? So we're calling a function convex, but convexity is more naturally stated for a subset of Rn, right? So what is the connection between calling a function convex? So is there some corresponding convex set? The answer is yes. So f is convex if and only if epigraph of f is a convex subset of Rn plus 1. Or if I like, I would like, I prefer to write it as Rn plus R to show that this is my domain and this is the place where the values of f are there. Okay, so what are some examples of convex functions? The most simple example are affine functions. All right, so you have Rn to R, and you have a vector u in Rn, and you have a scalar alpha. So f is of the form f of x is equal to u dot x plus alpha. So this we saw, yeah. So this, yeah, it's clear that it's an affine function. You can check from the definition. And a real valued function will be affine if and only if f and minus f are both convex. Okay. And the second thing one has to keep in mind that the supremum of arbitrarily many convex functions is again convex. So that is, I'll leave this as an exercise for your assignment. So the supremum, if you can start with just two, let's say if you have two convex functions. So the whole point will be essentially you have f1, let's say x plus y over 2 is less than equal to f1x plus f1y over 2. By the way, this is also an equivalent definition of convexity. Remember, when in convex sets, there are two ways we defined it. One was saying that for any lambda, you have lambda x plus 1 minus lambda y is also in there. Or you could say for any x and y, the average midpoint is also in there. And then once you have that, inductively you can show that, okay, given x, y, the midpoint is in there. So these two, this midpoint is in there, this midpoint is in there. So essentially the dyadics, meaning everything like k over 2 to the n. So all those points will be in your set, and if it is not disconnected or anything, then you'll have the whole line is also in there. Okay. So similarly, convexity for a function also you can define in this manner. So you have two convex function. And the claim is that if I take maximum, pointwise maximum, so max of f1, f2, it also satisfies this property for xy in that domain. Yeah. Yeah. Anyway, like this D. So here the continuity argument was essentially because D is a domain. So if I take, there is a ball around it which is completely contained in D. So if all these points are in there, then of course the whole segment is also in there. Anyway, so those are some details you have to check. But yeah, the point is for two functions, you can actually immediately show from these inequalities that maximum of f1 and f2 must also satisfy this. Okay. That's simply because you'll have maximum of f1, f2 evaluated x plus y over 2 is less than equal to maximum of this, but then that will be less than equal to the individual maximums. Okay. And actually, so you may think these are special examples. We started with an affine function and we gave a recipe of constructing more convex functions, right? Affine functions are convex. So if I take supremum of affine functions, then I should get more convex functions. As it turns out, that is the list of all convex functions. So I'll state that as a theorem. Every convex function f from omega to Rn is the supremum of affine functions. So the second recipe is in fact an exhaustive recipe. You have no more. And the proof, I will not prove it in general. I'll prove it for one dimension and then you'll immediately see. So again, I might leave this as an exercise in the assignment. So this is something like a affine function, sorry, something like a convex function. So the epigraph, so this is the epigraph, right? So epigraph meaning all those points where f of x is less than or equal to xi. So if you have a value here, all these points correspond to the epigraph. So this whole set is the epigraph. Epigraph is convex. If a function is convex, if and only if its epigraph is convex. Now, we have proved a theorem for closed convex sets that at any point on the boundary, so this is on the boundary clearly because if I take a ball, this value xi might be there, but there will be some values which are less than that, less than the value in the graph, just by looking at this interval. So this is definitely a boundary point. But at any boundary point, we have a supporting hyperplane. We have proved this result. And in fact, we have an exhaustive because of the separation theorem. So we need both theorems. We need the supporting hyperplane theorem and we need the separating the separation theorem. If we have a point outside of it, then we can always draw an affine function which separates this epigraph and this point. So the list of supporting hyperplanes is in fact exhaustive, meaning it completely determines this convex set. If I take intersection of all these closed half spaces, I will get this epigraph. So, and that precisely corresponds to the supremum of the affine functions. Because if I have a hyperplane like this and I'm looking at this closed half space, then in fact what I'm saying is, yeah, the epigraph is completely contained in here. So which means f of x. So in particular, the whole graph is contained in here. So that means f of x is bigger than or equal to this u dot x plus alpha for all x. So if u was the corresponding affine function, then I have this. So now essentially when I'm taking suprema, I'm talking about intersection of all these closed half spaces. So that will give me precisely this epigraph. And of course, that will also determine only the boundary here. So using this geometric idea and the supporting hyperplane theorem and the separation theorem, you can conclude that every convex function is in fact exactly equal to the supremum of a given list of affine functions. Okay. All right. So I think this is a good place to stop today's lecture. So tomorrow, not tomorrow, next class on Tuesday, we will study more properties. In fact, we'll make certain extra assumptions on F, like differentiability and so on. You might remember that for functions on for real valued functions on R, and let's say they're differentiable, let's say twice differentiable even, then their second derivative must always be bigger than or equal to 0 for convex functions. Or if they're once differentiable, you can say the derivative is in fact monotonically increasing. So all these results you can find in Rudin, like Principles of Mathematical Analysis. Perhaps you have covered that in class, but we'll repeat that. And based on this intuition in one dimension and looking at directional derivatives, we can make such assertions for convex functions in higher dimensions. For example, one result will be that the Hessian should be positive definite, which is the equivalent of saying the double derivative is positive in the one-dimensional case. So the equivalent version in high dimension is that the Hessian should be positive. And all these quadratic functions in like least squares methods and all we'll see, there the Hessian always turns out to be positive. So that's another example of a convex function, and which is a very important example that we will want to consider. Yeah, so we'll be proving all these results from multivariable calculus. Maybe we'll review a little bit about like Taylor expansion, total derivatives, and so on, which you are parallelly doing in your multivariable calculus course. All right. So see you next week.